Hi again. Thank you for making the first step into your data science journey in Python. Before we start Python programming in week 2, we'll start our course by reviewing what data science is and how we conduct data science research. By the end of this video, you will be able to describe what modern data science is, explain why data science is the key to getting value out of data and where the growing interest for it comes from, and list a recommended set of skills for a data scientist. We have all heard it. Data science turns data into insights or even actions. But what does that really mean? Data science can be thought of as the basis for empirical research, where data is used to inform our hypotheses and provide observations. In many cases, this data is used either by businesses or by scientists to inform their understanding of a phenomenon. Because there are often large troves of data which we can mine for insights, we often call this big data. Insight is a term we use to refer to the data products of data science. It is extracted from a diverse amount of data through a combination of exploratory data analysis and modeling. The questions we ask are sometimes quite specific, but sometimes it takes looking at the data and patterns in it to come up with a specific question. Another important point to recognize is that data science is not a static, one-time analysis. It involves a process where the models we generate lead to insights, and those insights are then improved by gathering further empirical evidence, or simply data. For example, a book retailer like Amazon.com can constantly improve the model of a customer's book preferences using the customer demographics, his or her previous purchases, and prior book reviews by the customer. Their models also likely take into account the similarity of customers to detect common interests. The book retailer can also use this information to predict which customers are likely to like a new book and take action to market the book to those customers. This is where we see insights being turned into action. As we have seen in the book marketing example, using data science and analysis of the past and current information, data science generates actions. This is not just an analysis of the past, but rather generation of an actionable information for the future. This is what we call a prediction, and it is very similar to a weather forecast. When you decide what to wear based on the forecast for the day, you're taking action based on insight delivered to you. Just like this, business leaders and decision makers take action based on the evidence provided by their data science teams. Because companies take action based on these insights, data science teams need to be experts in their practice to ensure those insights are well reasoned. You've likely just begun hearing more from the media about data science and from employers about the demand for data scientists, so it might seem like data science came out of nowhere. However, data science has been around for a very long time. Scientists have always used data to gain insight based on observations. So why then is data science suddenly on the rise? The answer lies in two things. First, our ability to collect data in real time has ballooned with data coming from a variety of places, including real-time environmental sensors, websites, smartphones, and a variety of other sources. In turn, this influx of data has increased demand for large-scale data processing. This data growth, combined with the advances in storage, networking, and computing at scale, has brought us to a new era of data science. Many dynamic data-driven applications in this new era build upon data-driven predictions to support decisions, just like the Amazon book prediction example we discussed. It is nearly impossible to find an industry, scientific discipline, or engineering endeavor today that is not impacted by data science. One need only look at the major trends in smart cities, precision medicine, energy management, and smart manufacturing to see how it is shaping our economy today. And all these fields are looking for experts in a combination of advanced data analytics with traditional modeling and simulations. We started by saying that we are collecting more data than ever before. But how much data and in what form are we really talking about? Let's take a look. The data can include anything from user preferences and purchasing history on websites to scientific data from remote sensors and instruments and personal health data from wearable devices and social media data related to customer satisfaction, political trends, health epidemics, law enforcement, and terrorist activities, as well as medical data from drug trials, treatment options, and patient population. This is probably already sounding like a lot of data, but we could look at this differently. If we look at just 1 minute on the internet, we'll begin to fully grasp the massive size of data produced and data stored every minute. Every minute, 204 million emails are sent, 200,000 photos are uploaded, and 1.8 million likes are generated on Facebook. On YouTube, 2.78 million videos are viewed and 72 hours of video are uploaded. It is not any different for scientific data. HP ran the high-performance wireless research and education network that only connects sensors in San Diego, Riverside, and Imperial counties, collects 30 terabytes of data annually. We use HP-RAN data collected from weather stations throughout San Diego County for wildfire monitoring and modeling. This consists of daily amount of 0.5 gigabyte environmental sensor data and 4 gigabytes of camera data throughout 18 stations. This may not sound like a lot, but this is just one system for 3 counties. NASA's MODIS, or Moderate Resolution Imaging Spectroradiometer, is a satellite that has imaging instruments on 2 satellites called Aqua and Terra. MODIS instruments on these satellites capture images of the entire surface of Earth every 1 to 2 days, acquiring data in 36 spectral bands. This equals 40 science products and produce 600 gigabytes of data per day, which equals 219 terabytes of data per year. It's not that different in precision medicine. One of the key promises in precision medicine comes from using individuals' genetic profile to guide decisions regarding prevention, diagnosis, and treatment of disease. Genome sequencing is only one part of data, and it needs to be augmented with treatment data, medical histories, and other biomedical data. According to a Fast Company article in 2016, only the genome sequences of people who will be diagnosed with cancer was predicted to equal 4 exabytes. That's a lot of data. Other large volume data sources in scientific research comes from LIGO, Deep Space Network, and Protein Data Bank. LIGO, the Laser Interferometer Gravitational Wave Observatory, is the data source that led to the gravitational wave discovery in 2016. The experiment provides large-scale physics and observatory to detect cosmic gravitational waves. Deep Space Network, which is NASA's network of large antennas and communication sites located in several countries that are used to support space missions and research asteroids and planets, updates its data stores with real-time data every 5 seconds. Another research product is the Protein Data Bank, which is a repository of information about 3D structures of large biological molecules, which is important for research on human health and disease and drug development. Management and analysis of such scientific data sets is a huge challenge for modern scientific research. And in there, you heard me say words that start with peta, exa, and even yotta to define a size. But what does that all really mean? For comparison, 100 megabytes will hold a couple of encyclopedias. A DVD is around 5 gigabytes, and 1 terabyte would hold around 300 hours of good quality video. A data-oriented business currently collects data in the order of terabytes, but petabytes are becoming more common to our daily lives. CERN's Large Hadron Collider generates 15 petabytes of data a year. According to a report by IDC, sponsored by a big data company called EMC, digital data will grow by a factor of 44 until the year 2020. This is a growth from 0.8 zettabytes in 2009 to 35.2 zettabytes. A zettabyte is 1 trillion gigabytes, that is 10 to the power of 21. The effects of it will be huge. Think of all the time, cost, and energy that will be used to store and make sense of such an amount of data. The next era will be yottabytes, that is 10 to the power 24, and brontobytes, that is 10 to the power 27, which is really hard to imagine for most of us at this time. This is also what we call data at an astronomical scale. The choice of Milky Way galaxy in the middle of the circle is not just for aesthetics. That is what we would see if we were to scale out 10 to the power 21 times into the universe. Cool, isn't it? The bottom line is that all of these sources point to an exponential growth in data volume and storage. While many of us are excited by the opportunities offered by big data, this rapid growth also comes with a number of management and analysis challenges, least of which is information overload. Our challenges isn't just to manage the data, but to try to see how everything is connected. Finding the connections between the kinds of data sets we've discussed has the potential to lead to interesting discoveries. Such an endeavor requires proper use of data management, data-driven methods, scalable tools for dynamic coordination and scalable execution, and a skilled interdisciplinary workforce. This is where you come in the picture. By putting your time into skills in programming in Python, statistics, machine learning, and big data, you will be ready to take on some of the technical challenges in data science like drug effectiveness analysis, crime pattern detection, and self-driving cars. As a summary, a data science team often comes together to analyze situations or answer questions in business or science which no single person could solve on their own. There are lots of moving parts to the solution, but in the end, all these parts should come together to provide actionable insight based on data science. Being able to use evidence-based insight in your decisions is more important now than ever. This MicroMasters will provide you with related technical skills on Python programming, statistical analysis, machine learning, and big data tools to make this happen. Leo and I look forward to giving you the fundamental data analysis skills in Python that you'll use throughout the entire MicroMasters.